Hi everyone, welcome to this video where we are going to do, I guess we'll call it a video answer key, where we're going to go over your classwork problems and give you some explanations to things. So at the top we have a summary here of what each of the variables represent, as well as our three main formulas: how to find arc length, which is the total amount you're traveling in these circular objects, angular velocity, and then linear velocity. So starting with number one, it is a very straightforward. We want to find the angular velocity in radians per second of a vinyl record that spins at 33 and 1/3 revolutions per minute. So this is just going to be a unit conversion question. We're going to take that 33 point and we'll just say 33 revolutions per minute. So we want to convert the revolution into radians and the minutes into seconds. So we're going to do two different multiplications to change that. So let's start with revolutions. I'm going to put the revolutions down the bottom so that they cancel out, and radians up top. I know that one revolution is equivalent to 2 pi radians. The second calculation is I need to move my minutes up top so that the minutes unit cancel. And what do we want? Seconds. So 1 minute is equal to 60 seconds. So revolutions cancel, minutes cancel, and before we do all of our math, you'll see that we're going to end up having this in radians per second. So we're going to calculate this all out. In fact, I'll probably just plug this all into my calculator. So I'm going to type in 33.3 times 2 pi, get an answer from that, and then divide my answer by 60. And for all these examples, I'm going to go ahead and round our final answers to the nearest tenth of a decimal place. So this is about 3.5 radians per second. Now I know 3.14 radians is pi, so that basically means that this vinyl record is spinning about half a revolution every second or so. All right, that's it for conversion for number one. Now let's move on to something that has a little more in-depth idea. So Rausch Creek Trail in Pine Grove, Pennsylvania is a 12.6-mile off-road trail that is recommended to take 4 hours for us to drive. We're going to be driving a Jeep Wrangler that has a 31-inch diameter. Now, that's going to be important as we move into using the radius, and we'll talk about what that means in a minute. All right, so the first question is determine the linear velocity of the wheel in feet per minute. Well, we actually already know the total distance, which is 12.5 miles. 12.6 miles, I'm sorry, and our total time. So we're actually going to be able to figure this out pretty quickly. So right away, we're going to take 12.6 miles and we're going to divide it by 4 hours. This is going to give me my total velocity, but because we want this in feet per minute, we're going to have to do some conversions here. So first things first is we want to get rid of miles. So 1 mile is equivalent to 5,280 feet. And then hours will go up top, and we want what? Minutes. 1 hour is 60 minutes. So we're going to go ahead and run those calculations. I'm going to do 12.6 times 5,280, and I'll just kind of write my answer here for now so you guys can see it. That's my numerator. 4 times 60 is going to give me 240. We're going to divide those two numbers, so 66528 divided by 240, and we get about 277.2 feet per minute. Okay, one down. Let's move on. Oh, by the way, before we forget, we really should call this radius 31/2, just so that we don't forget as we're doing this. All right, the next question is we want to determine the angular velocity. Now, because we already know our linear velocity as well as the radius of the tire, I'm kind of feeling like the formula I want to use here is V equals R times omega here. Okay, which is our W. If I call it W, that's what I mean. So we already know V because V is just the 277.2. Our radius is 31/2, but we've got to pause this for a moment because that's actually not what I want to put in here. And here's why. 31/2 is actually given to us in inches, and because our velocity is given to us in feet, we are going to have to convert this 31/2 inches into feet. And so to do that, you always just divide by 12, okay? Because inches, 31/2, divide that by 12, and when I do that, we're going to get 31/24, and this is now the feet. This is how many feet. So it's basically a little bit more than 1 foot, okay? So our radius is going to be 31/24, and then we don't know our W. That's why we're going to solve for that. So to solve this, we'll multiply both sides by 24/31. These are going to cancel, and we're going to end up with an angular velocity of, well, let's see, 277.2 times 24 over 31. We'll end up with about, we'll round to the nearest tenth, 214.6. And now this is going to be radians per minute. Okay, so this is how much the wheel is spinning 214 radians per minute. Final question for number 2. What is the total angular displacement? So we know that every minute we're moving at 214.6 radians per minute. But what I want to try to do is figure out how long that is over the course of 4 hours. Well, let's keep in mind real quick that 4 hours, in terms, we have to stay in minutes because that's what our unit is. 4 hours is equivalent to, well, 60 minutes are in an hour, so 4 times 60 means that it's 240 minutes long. So I'm simply just going to take 214.6, multiply it by 240, and that is going to give us an answer here of 51,504 radians. Wow, that is a lot. Well, that would make sense. In a 4-hour drive, that wheel is going to spin a lot. If it actually makes you, if it helps to give you any perspective on that, if that in revolutions, because if you divide by 2 pi, or 6.28, whatever you want to call it, when we get that, we're going to get 8,201 revolutions. That's how many times the wheel is going to have to spin in order for this to happen. All right, let's move on and talk about the giant wheel at Maurice Pier in Wildwood. So once again, they're going to give us the diameter of the wheel. Most circular things are given as diameters, so we do have to take a moment and just remember that we have to divide that by 2 to get our radius, which is what we're going to use all of our problems for. So the radius is 78 feet for this wheel. And these are all real numbers, by the way. A complete revolution is done in 50 seconds. We would like to find the angular velocity. So let's start with the idea that we actually are given technically our revolutions per second. 1 revolution takes 50 seconds. But I want to obviously convert this to radian. So we're going to put that revolution and radian conversion here. 1 revolution is 2 pi radians. And so this is going to give me 2 pi over 50, which simplifies, by the way, to pi over 25 radians per second. Now we can leave that precise answer and use it later in our problem. But as a decimal, I got 0.125 radians per second. So this is going to be how much the wheel is spinning every second, radian-wise, degree-wise, angle-wise, whatever you want to look at. Now, we want to ride the giant wheel, and we want to travel through 1 entire revolution. Now, how far do you travel is going to tell me that we want to find arc length. So that's going to be our key thing here. So arc length formula is S equals R times theta. We do know the radius, once again, as we pointed out, is 78. Since we want to just do 1 revolution, that is equivalent to 2 pi radians, so we're going to use 2 pi as my theta. And so in this case, our S value, or our arc length, when I type it in and get an answer, it actually rounds out pretty nice. It comes out to about 490 feet. So when you take the ride in Wildwood on the Ferris wheel, you move a total of 490 feet when you do 1 revolution. All right, one more question to go with the wheel. What is your linear velocity when riding on the big wheel? Well, at this point, we need to know, in order to get velocity, we need total distance over total time. So in this case, we're going to take our velocity and equal S over T. That's what the formula says. Since S, our total distance is 490, we'll have to note that it's feet. And then 1 revolution, how long does it take to do that? It takes 50 seconds. So when I compute this, we're going to get 490 divided by 50, and that's going to be 9.8 feet per second. Now that's not the answer, because I do want to get the answer in miles per hour. So let's do one last conversion, and then we'll be done. So 9.8 feet divided by seconds. So when we're doing this conversion, just remember we have to get rid of feet and turn it into miles. We have to get rid of seconds and turn them into hours. So 1 mile is 5,280 feet. 1 hour is equivalent to 60 seconds. So we're going to multiply, actually 1 hour is not 60 seconds. 1 hour is actually 60 times 60, so it's actually going to be 3,600. Okay, so keep that in mind. We've got to be careful with that. And when I compute this all out at the end of the day, we're going to end up with an answer of 6.6 miles per hour. Now just think, a brisk walk, if you were walking, is about 3.2, 3.3 miles per hour. So you're moving a little faster than a brisk walk, probably a jog. okay, of sorts. That's how it feels as if when you're moving on the Wildwood Ferris wheel. All right, one more question to go before we wrap up. We have 5 minutes before this timer runs out on this video, so let's move it to the carousel at Hershey Park, all these amusement rides. We already know our angular velocity, except it's in the wrong unit, so we're going to convert it to radians. And we also know, once again, the diameter, which, once again, the radius is just going to be half of that, so it's 25 feet. Okay. There's also one other element to this, and that's the idea that when you ride on a merry-go-round, or a carousel in this case, we have an outer ring that has seats and horses, and we have an inner ring. So we're going to have to talk about that in these problems. But let's start with letter A, because we do have to figure out what 6 revolutions per minute is as a radian. We've done this a few times already in this video. We're going to convert radians and revolutions. So this is just going to give me 12 pi radians per minute, which we now can start using in problems. That as a decimal is 37.7 radians per minute. Okay, great. 1 down, 3 more to go. It says, your friend rides one of the horses inside of the carousel, and you ride on the outer ring of the carousel. Determine the linear velocity for both of you. Okay, so let's start with this idea that on the outer ring, okay, the outer ring, as it's pointed out in the very beginning of the question, is 20 feet from the center. So if we want to calculate the outer ring and we want to figure out the velocity, now there's 2 versions of this. The one that I think we should use here, since we know angular velocity, is v equals r times omega. So in this case, the velocity would be your radius, which in this case is going to be 20, and times our angular velocity, which is 12 pi. We're going to multiply those together. We're going to round it, and I get an answer of 753.6 feet per minute. So every minute you will be moving on this carousel ride about 753 feet. Now we go to the inner ring, and we know that even though it's going to have the same angular velocity, it's because of the different radius that you have, or how far you are from the center of the carousel, it's going to change the question. In this case, the radius is now 10, since we're only 10 feet away from that fixed center, but we're still going to use the same 12 pi, since angular velocity will never change. So when I multiply this out, I get about 376.8 feet per minute. All right, halfway there. There's our answer. Let's move on to letter C. The ride lasts for 5.5 minutes total. What is the total linear distance you travel? So in the outer ring situation, we know that we traveled 753.6 feet every single minute. So all we need to do to find this is multiply that answer by 5.5, and we get an answer of 4,144.8 feet. So you move almost, well, a mile is 5,280 feet. So we're kind of like reaching close to a mile of riding when we're taking that wheel. But look how much smaller, I should say, the inner is going to be here. So we're going to take that 376.8, and this time we are going to multiply it still by 5.5 minutes. In this case, it's almost half. So if you really want to get the best bang for your buck here when it comes to riding the carousel, you need to be riding that outside ring. That outside ring is going to be much more enjoyable if you want to feel like you're moving faster. All right, final question for this video is, later in the day, you notice the carousel operator has slowed the wheel. We are now slowing it to 4 revolutions per minute. We'll calculate what that is in a split. If you were to sit on the outer ring for this ride, because you know we want to ride on the outer ring, that's the best place to be, what would be your linear velocity? Well, let's figure out what our angular velocity is first. So we have 4 revolutions per minute. We're getting used to this now. We're going to do radians over revolutions. 1 revolution is 2 pi. So this is going to be a total of 8 pi radians per minute. All right, so now it's time to figure out our linear velocity. Once again, I think using r omega is definitely the smart way to go here. Since we already know our radius, in this case is 20, since we're sitting on the outer ring, our angular velocity is 8 pi, and when I calculate this, we'll round to the nearest tenth, I get 502.4 feet per minute. Now remember earlier we were going 753, so when the ride slowed down, we slowed down by about 200 feet per minute. And that will conclude this video. Hope this was very helpful. Please feel free to go back to any other parts of the video you'd like to see. And with that, you guys have an awesome day.